out any questions at any time, enter your questions into the questions window of the GoToWebinar interface. And if your audio drops out,
and
call
welcome
into
to
the
the
1-800
VGA
number.
meeting on Aramag interpretation. This all started with a book by our keynote speaker, which then turned into an SEG lecture tour, and by great good fortune, David offered to give the talk in London, and at my co-chair Sheila's suggestion, we turned it into an afternoon seminar. She also used her good offices to get us sponsorship by the VGA, and therefore the use of this building for nothing, which is why you're paying nothing. Speaking of paying nothing, Bridgeporth are providing the refreshments, which will be in due course partaken of. Thank you very much. And Gearsoft are providing the webinar facilities. You want to be conscious of this. Other than that, we've got a better sound system than we might have had. But there are rather more people listening in than we have here. What's the current count? Okay, there's over 500 pre-registered, but anyway, there's more people listening out there than there are here, and we'd like to welcome our remote guests as well. Let me see. Oh, yeah. We are very happy to see the great spread of people we do have here, people who've made the effort to come from Ireland and from Scotland. But I'd just like to mention Derek Morris, who is perhaps in some sense the senior member in the room. For those of you who are old enough with long enough memories, Derek was geophysics manager for hunting surveys up to about 25 years ago. So he goes back a long way, and we're very happy to see you here, Derek. I'm going to hand over to my co-chair now for the next bit. You can stay right there, Sheila. Change this slide. There we go.
Thank you very much. I'm Sheila Peacock, and I know almost nothing about geomagnetism. However, I'm co-chairing this meeting. I want to welcome you all on behalf of the British Geophysical Association, which is a joint association of the Geological Society of London. They have offices over there, and the Royal Astronomical Society, in whose offices you now sit. And so if you belong to either of those societies, you can join the British Geophysical Association merely by telling them that you want to be a VGA member. There's no further fee. And we exist to promote geophysics in the UK, and so we do that by, among other things, organising meetings like this one. And we also, I personally am trying to raise the political profile of the British Geophysical Association by trying to arrange that we chip in and have our say when our parent societies are providing output to inquiries by the House of Commons, by NERC, and other UK establishments that are going to influence life for geophysicists. I want to say a great welcome to all the people who are online, but the following does not concern them. This is the mandatory announcement about fire precautions. If the fire alarm goes off, please assume that it is a fire. Nobody has told me that we're having any tests. You should leave the building as quickly as possible, leaving behind anything that will impede you or other people. And you can go out through the archway on Piccadilly, turn left, go along to Sackville Street. Then it's just round the corner in Sackville Street, there is a bookshop. And outside that bookshop is the assembly point. I assume that it is there so that we are well out of the way of the fire brigade, who I hope would come in a great rush to put out a fire in such a wonderful historic building. So just to repeat, if there is a fire alarm, out through the arch, left along Piccadilly, left again up Sackville Street. And hoping very much that we do not need that information. And with that, I will introduce our first speaker. Yes, I want to yes.
mobile phones off, please. If your phone rings during this meeting, you owe the speaker and the co-chairs a drink, right? For the discourtesy of interrupting. Phones off. If you're anywhere near a radio mic, I mean really off, because even the silent ring affects radio mics.
Yes, thank you very much. I had forgotten that. Yes, to introduce our keynote speaker, the reason for our having this meeting is to welcome David Isles from Perth, Australia. He works for TVT Consulting and also for Southern Geoscience. And he has just completed his term as the 2013 Honorary Lecturer of the Society of Exploration Geophysicists. That's the American Society of Exploration Geophysicists. And so this talk isn't part of his STG series, but it contains some of the material that was presented there. And he is going to be talking about geological interpretation of aeromagnetic data. Thank you very much.
Thanks very much to Sheila for the introduction, and to Alan and Sheila for putting this whole show together. Quite flattering to have just the audience that's gathered here to listen to my same old story. It's even more flattering to have a whole bunch of people out viewing on the internet. So welcome to you, and welcome to them. Find the start button. We'll be away. My talk is geological interpretation of aeromagnetic data, and I'll say geology and geological a lot during the talk. As Sheila mentioned, the talk is the outfall of a book, which is recently on the streets, and the graphic there pretty much says what the book is about. It's about starting with geology and moving up through layers of work and recording to an integrated product that integrates the geophysics, in this case we're dealing mainly with aeromagnetics, with the geology for all purposes, for all exploration purposes, and I'd include government geological mapping, groundwater exploration as an exploration purpose. The course has kind of grown out of the careers of myself and a few colleagues, and the integration side of things, I guess, is what we all do for a living. So let's just look at how I'm going to present this. I'll start with an overview of just the things that we can do with aeromagnetics, and that'll come back to well, the common thread really is mapping geology. I'll then talk about our methodology of interpretation, and that's probably the most important part of the talk. It really kind of says this is the way we actually go about this task. Then got two case studies, one from Galmoy, the zinc-lead district in Ireland. The other is a much more routine, standard oil exploration study onshore oil exploration study from Central Australia. And then I'll say a few concluding remarks, which will be a little bit of a banner wave for Australian aeromagnetics and Australian geophysics, but I'm sure you'll permit me to do that. So let's just address the question, what can we do with aeromagnetics? And finding ore bodies is probably what we think of, as we study geophysics at university and say, well, aeromagnetics is a tool that finds particularly hard rock ore bodies. And here are 6 tier 1 examples. What I mean by tier 1, it's a term I think invented by BHP that meant no matter what sort of poor management or what sort of poor economic conditions, this ore body will make money for a long time. So each of the ore bodies in here is a Rio Tinto BHP extrata sized ore body. And unfortunately, I haven't got the 6 or 7 hours that it would take to go through each one individually. But what we can say is that finding the ore bodies in these frames is not about finding a bomb. It's not about geophysical anomaly, a magnetic anomaly that stands out, hits us in the face, and we say, let's go and drill that. It's about careful observation, integration with the geology, and application of the local geological themes. We'll come back to this slide a little bit later, but I think some of you probably recognise some of the ore bodies. Most important thing is that none of them is a standout magnetic anomaly, but all of them could be found with the help of magnetics. And in some cases, if you had taken away the aeromagnetics, the ore body would still be in the ground undiscovered. And the similar thing applies in petroleum fields, not perhaps so much. Increasingly though, we're finding that there is an enormous amount of geological signal in aeromagnetics in sedimentary basins, and more we're finding that that becomes pertinent to oil field scale. And I'll show you some examples of how that works in sedimentary basins as we go along. But in each of these fields, each of these areas, there are really strong geological signals contained in the aeromagnetics that help to guide exploration. And those signals, again, are not sort of direct anomalies. It's a matter of understanding what they mean in the context of the geology, integrating them with the geology to push the exploration forward. So the answer to the question really is that aeromagnetics maps geology, and most geological environments are going to reveal critical information through the eye of the magnetometer, and that's the theme that we'll pursue. So if we're talking about mapping geology, it's a very kind of broad term. What do we mean by that? Lithology, can we see different signatures, different contents of magnetic minerals in different lithological types? Of course we can. Structure, can we see breaks in the pattern, folds and bolts and discontinuities? We're used to doing that. So drawing lines on maps, seeing structure, seeing geometry, that's all good. Alteration processes, be they in oil fields or in mineral fields, do they change the nature of the assemblage of magnetic minerals? Certainly do. And metamorphism, same sort of deal, where we have changes in pressure and temperature, changes in mineralogy, and particularly the magnetic mineralogy. And of course, mineralization is kind of another very, very broad term. And if we're looking for mineralization, we're probably going to have all of these attributes somehow tied up in the story. So mineralization is an attribute. Yes, we expect that there'll be some clues there that we can see in the aeromagnetic signal. How and why is it possible? I guess the most important thing is that magnetic minerals are present in almost all rock types, and this is kind of something that doesn't come through in our old conventional textbooks. But if we look at the rock record and we look at different classifications of rocks, and we see the work of people like David Clark and others, there are measurable amounts of magnetic mineral in all sorts of sedimentary rocks, as well as as we'd expect in igneous and metamorphic rocks. And importantly, the kind of detection limit in terms of concentration of magnetic mineral is really, really small. It's 0.0003% magnetite detectable in a sensible volume of rock in an airborne survey. And getting to that survey, the signal levels that we can now confidently have in our final data are down around a 20th of a nanotesla. That figure's probably maybe half or less of what contractors will pitch at and kind of hope that you want. But with care and attention, a grid with a noise level that's less than a 20th of a nanotesla is achievable. The other thing, which is, I guess, is the historic thing that people look around the globe and see that there are aeromagnetic surveys in all sorts of places and covering very large areas, why is that so? Um, it's so because with an airborne magnetometer we can cover large areas very rapidly and in a large amount of detail. And I put a small note there on the commercial side of it, which is probably going to be outdated in 10 minutes. But in the context of exploration and general mapping, the cost of doing aeromagnetic coverage is really, really small. So we can cover large areas, we can do it in detail, and the cost is actually quite small. Let's have a look at some different terrains just quickly as we should. An igneous terrain, the Charters Towers area in North Queensland, as we expect, an area dominated by, in this case, intrusive igneous rocks, has got a complex mixture, a pudding of different magnetic signatures. No surprises there. Metamorphic environment, go back to my homeland at Broken Hill. Most of the rocks at Broken Hill started life as sediments. So what's happened here is that iron-rich sediments have been subject to pressure and temperature. The iron-rich minerals have been converted to magnetite-rich minerals, and the whole province, if you like, has been lit up by that metamorphic process. And this is again not unexpected, but you can see the impact of metamorphism and the magnetic minerals gives us I guess a full picture of what's going on in that part of the world. And then we come to sedimentary terrains, which traditionally have not been the hunting ground of magnetometers. And I use an area from South Australia, which is a historic area, the Flinders Ranges, the Adelaide Geosyncline. Adelaide Geosyncline, very famous area of the youngest Proterozoic, a sedimentary pile of 20 or 30 kilometres, amazing rocks, amazing topography. The earliest main mapper was Douglas Mawson, and the fact that it's beautiful countryside, beautifully exposed, and wonderful sedimentology means that any geologist that goes to South Australia will go to the Flinders Ranges and do some mapping. So we have a situation, a large area of wonderful bushwalking and camping and geological mapping that many geologists have worked in over a period of 100, 120 years. So it's beautifully mapped, beautifully exposed, and you would ask the question, well, is this an area where magnetics can really do any good? And historically, when the South Australian government was embarking on its program to fly the whole state, the question arose as to whether it was actually worth flying the Adelaide Geosyncline because it's there, it's in your face, it's exposed, it's well mapped, and to their credit, the managers of that program said, well, we should do this, and the result is something like this. And this is there's a scale bar there. This is 400 metre data, so it's in Oz it's kind of the standard government spec type coverage. But the impact of this data on that beautifully mapped area has been really quite substantial, particularly from the exploration point of view and understanding the different facies of things. Most of the rocks in this area are just siltstones. So if you go through the legend on the geology map, it's ABC siltstone and down to XYZ siltstone. Mainly it's fine grained sediments, but a range of magnetic signatures that really add not just to the exploration context, but also to the understanding of the sedimentology and the whole geological story. So that kind of brings us to in terms of talking about terrains, to the sedimentary rocks do have measurable signals, and we'll see some much younger rocks, sedimentary rocks that do. So my statement without proof, but a little bit of demonstration, is that sedimentary rocks of all ages have, have measurable magnetic signals. And then we can talk about scales. I think Alan and some colleagues were partly responsible for building an aeromagnetic map of the globe. In Australia, we're blessed with complete coverage at line spacings, I guess most commonly 400 metres, some out to 1.5 kilometres. But you can see this image of the entire continent presents to us the opportunity to analyse Australia at a continental scale. So my friends and colleagues in Geoscience Australia in Canberra use this use this data and this image as really their cornerstone for the work that they do at broad scales. They have good geological mapping, they have quite good gravity, they have seismic, but the aeromagnetics, and particularly in its uniformity and continuity, allows them to pull all of those data sets together into one story very, very well. So continental scale using magnetics, I guess that's no surprise to many of us. What might be a surprise to some is that we now come down to mine scale. So airborne platforms, fixed wing platforms flying 20-metre line spacing in the mine environment produces information that, let's stick to this side, that is actually pertinent at pit scale. It shows things that mine geologists may not have noticed in their day-to-day work, and that's pretty important. And as you can imagine, as we open the line spacing out, the scales that we work with become more broad, and I guess the limitation of our scale of investigation is also controlled by what size of area we've flown. The important thing is that the line spacing really controls the scale that we work at, and the old established from hard experience rule is that the scale that we can push an aeromagnetic data to is around about that where 1 centimetre is a line spacing. So for our mine scale work, flying at 20 metre line spacing, usually around about 20 metres off ground, we can work at 1 to 2,000 scale, and that is useful information in a mine environment at pit scale. And obviously, as we've got larger and larger surveys, probably with broader and broader line spacings, our scale regime changes. How deep? Again, we have large volume data sets that show us very, very long wavelength aeromagnetic anomalies that we can, just from the basic physics, deduce deep. The limiting factor, of course, is the Curie point. So Curie point depth, in some places less than 8 kilometres. In old cold continents like Western Australia, it's greater than 20 kilometres. And I guess that space from surface down to the Curie point is where we have rocks holding magnetic properties. And the question then is, well, it's all very well for them to be there, but can we see them? And that answer is yes. Those of you who have been involved in oil exploration magnetics will be no surprise to you that that we see deep. And in fact, the earliest applications of airborne magnetics were to map basin architecture by simply determining depths to basement. And here's one of the examples I'll show a little bit later on, where it's from the Amadeus Basin in central Australia, where we can see lots and lots of very high frequency shallow stuff, but also some very significant broad features that we would deduce are from deep depths. The way to kind of quantify those depths in many ways, but the simplest and best established is just by modelling. And here's some modelling that's been done for that demonstrates that the long wavelength features here are consistently down the order of 15 to 20 kilometres. So our search space then is pretty much from surface down to the Curie point, provided we have sufficient sufficient volume of magnetic minerals in our rock bodies. So that kind of says that the uses of aeromag really span the entire spectrum of field mapping and exploration, from line scale out to continental scale and beyond, and covering pretty much the full range of depths that our normal kind of oil and gas exploration and mineral exploration would take into account. Okay, so that's kind of the overview, and it kind of says, well, you know, mag can do everything anywhere, and that's not entirely true. But let's just come back to reality and just look at how we use magnetics, how we actually take the magnetics from a survey and a bunch of images to a product that is, if you like, our end product that we're going to use, our mapping product, our exploration product. And there's a methodology that myself and colleagues have developed over the years. I'm not going to talk through each of these dot points. All I'll say here is that the parallels between the tasks that we do in what you might call mag-interp, or you might call just integration of mag and geology, are very strongly aligned with geological mapping. So we can kind of think of the geologist with boots and GPIC wandering through the fields, hitting rocks, recording what he or she sees, and basically making observations and building a picture which will then be put together into some kind of geological story. The way that we approach magnetics is much the same, and I'll show you that in a second. But the important thing from our aeromag perspective is that we approach this in much the same way as the geologist approaches mapping. We start with a bunch of observations, often observations that are not particularly clear to us as we're doing them. We then put all those observations together and put together some kind of draft map, and then we try to work out an interpretation that expresses how we see that array of geology forming. So how did it get to be like this? What might this mean in terms of exploration? So there's kind of a basic sort of hard work layer of simple and empirical observations. There's then a fairly standard compilation stage, and then there's a third stage where we allow our creative juices to flow and say, well, this is what we think it might mean. So let's have a look at an example of how that works. And the example's from the Pine Creek Juicing Incline in Northern Australia. It's a gold exploration area, and importantly, it's a small area. So we're going to be looking at an area of 7 by 10 kilometres, mainly sedimentary, but it's a let's just say it's a gold exploration area of some value. And we can look at the geology map, which is always our start point, and say, well, okay, we've got a small area, we've got good exposure, it looks like it's well mapped, and I can say that it is. Predominantly low-grade metasediments. Is mag going to really be very helpful to us? We can see much of the structure. Those of you who are involved in gold exploration can look at that and say, well, I can probably pull a few targets just out of that geology map. Why would I bother applying magnetics? And the data that we're going to see is shown here. 200 metre, not particularly detailed, and you think, okay, well, that small amount of line kilometres, so in this area there's 385 line kilometres of data, and in the commercial context, that's a fraction of a day's flying. So it's a fairly small amount of data, added to an area that's relatively well mapped. And if we sort of jump forward to the point where we say let's produce something that integrates the newly flown magnetics with the geology, we can do what in a matter of hours, what I'd call a quick interpretation. And here's an example of that. And it looks okay. You can see that we've filled some gaps, we've added a bit of continuity, we've kind of imposed a slightly different bent on the structure. And conventionally, you'd look at that and say, well, what's the problem with that? That's fine. We've taken some geology, we've added some geophysics in the form of aeromag, and we've got an expanded story. But my question is, can we do better than that? Can we spend more time and effort and get more out of it? And as you'd imagine, my answer is yes. A couple of points here. One is that I think these days we take for granted that the data acquisition, data processing, imaging side of things is covered. It's good. No matter where you draw it from, no matter what contract is used, no matter what software you use, in deference to Geosoft, and once again, thanks to Geosoft for sponsoring the webinar. We can take this part of this pre-interpretation part of our work and be quite confident that that's been done very well. And so, okay, so we've got a range of images, and in any project we'll normally pick what I call a set of workhorse images, which might be our favourites, or might be the ones that best suit that geology, and we'll look at it and we'll make observations. And a couple of things to notice about this observation layer of mine. It's not a particularly neat thing, and it's the analogue of the field geologist's field book. He goes around or she goes around and makes notes and tips and strikes and marks things on aerial photographs. And as it's happening, as it's evolving, it doesn't particularly make a whole bunch of sense. It's really just a collection of observations. And when you're doing these things, when you're drawing these little worms and squiggles and breaks, you're thinking about the geology, but you're not really understanding how they all pull together. And this is a great example where taking it from maybe a couple of hours' work to several days' work, and in the observation stage might be a full day or a little bit more, depending on how much you know about the geology. You can see all sorts of things, and I'm not going to bore you with all the local detail, but let's say there are features here that are showing structure. You can see little breaks in things. There are features that occur in locations that just don't make geological sense, so they're geological anomalies. And if I can go back, which I probably can, we can see things like this, that which is also expressed as this, that look quite funny. Odd, fuzzy, looks like a bit like a donut. It turns out that that's an alteration zone. As we're observing, we don't know it. As we're observing, that thing is really just a perimeter of some kind of fuzzy response with a funny little donut hole in the middle. So the range of different things that we'll record without actually knowing what they are until we get to this next stage of cross-referencing all the things that we've observed with the geology. And that actually takes a lot of time, and it invariably involves quite significant conflicts between what the geology is trying to say and what the aeromag seems to be saying, and that is a time-consuming headache that needs to be gone through. And I guess one of my hobby horses is that the information that we're looking at in these two panels has come from the same source. It's all coming from the geology somewhere. So somehow there is a reconciliation of these two data sets that is real. The fact that sometimes it takes us ages to try and work out what it is doesn't mean that one data or the other should take precedence or be right or wrong. The integration needs to be done, and it needs to be kind of acknowledged that, well, there must be an integration because the aeromagnetic observations that we've made come from the geology, the geology's come from the geology, so they must somehow bolt together. So we go through that and we create what I call a draft solid geology. I call it a draft solid geology because it's desktop work, and we come up with a whole bunch of stuff that is new and additional to the geological mapping, and it looks great, but until it's actually ratified with some form of in-field testing, it's a draft. It's a desktop thing. And so that's stage two, just compiling all the data without really having the story developed. In this case, the gold exploration story. We've got a new solid geology map, and you can see that we've added an enormous amount here. Not just structure, but obviously the filling the gaps here and adding a whole bunch of folds and quite detailed faults is important. But we've got an alteration zone. We've got certain anomalies. I guess the main theme here, though, is that we've added a layer of continuity and coherence to the geology, and starting from a point where it was pretty good. Okay, now if we're an explorer and we're wanting money from an exploration manager or an investor to go exploring and testing our ideas, this draft solid geology is probably not going to cut it. It's a scrappy looking thing, it's hypothetical, it doesn't have any field testing, and we need to build a story into that to attract the interest of the sort of people who are going to fund our exploration. And that's another layer of time. It usually involves, as I said, exercising a little bit of interpretive license, throwing our theories into say, in the context of gold exploration, our theories, our models of that particular area into the pot, and developing our interpretation to something that is not only presentable, but it has a story behind it. And if you think in terms of exploration management, saying, okay, well, here's our story, and it's got thrusts, and it's got folds, and it's got faults, and it's got anomalies and alteration zones, and it's got targets, and we can get excited about this, but probably not so much that. And if we build the local story of exploitation, in this case it's gold, it could be groundwater, it could be oil and gas, into that developing kind of model or theory, we then get to the targeting stage. And you can see with our thorough interpretation, I've just distilled this down to my 5 favourite targets. It's a presentable thing from your point of view. You haven't been through the thinking in the geology, so I could probably draw circles anywhere. But let's just say that number one, this is presentable. Number two, each of these yellow ellipses here has quite a good story behind it. And it's not just fault intersections. There's the theme of what's driving the gold mineralisation in the district. So each of those ellipses has its own little story and, if you like, its own little budget that we pitch for. And in terms of attracting the support to do that, it's a good product. And that's the several days effort. If we go back to the several hours effort, really we are missing a lot of detail. So if we don't spend the time, we're going to get limited exploration value. We're going to miss a whole bunch of important detail that's there in the measured mag data, but we haven't really taken the time to capture it in observation stage or interpretation stage. So I guess the theme then is there's a simple process of observation, a relatively simple geological integration process of putting that together into a revised solid geology, and then the exploration thinking of okay, how are we going to exploit this data? And the bottom line then really is that to get the value, you really have to spend the time. And the essential actual ingredients there are not particularly high-powered. It's really about geological thinking and the right application of time. Okay, let's have a look at some other studies. Galmoy is a zinc-lead district in Ireland. I thank London Mining for making this data available to me for the study. It turns out that this, in my almost 40-year career, is probably the most interesting data set I've ever worked with. There's not much to see geologically at surface. The Galmoy mine is here. The Lachine mine is here. These are peat strips, and it's beautiful, beautiful farmland, as we see when we fly it with quite detailed magnetics. And this is 100-metre line spacing. The scale bar is there. And what we see when we fly a mag is an intensity range of 60 nanoteslas, which ain't all that big. And most of that intensity range is taken up with these measles that appear in the survey area. And as you can probably guess, they relate to mostly farming infrastructure. There are sheds, there are tractors and harvesters, and all sorts of things that gobble up most of that 60 nanoteslas. And there's a regional gradient. The key thing there is the prospect of actually getting useful geological information out of this, particularly for shallow zinc-lead exploration, looks pretty grim. And it turned out at the time that wasn't an acceptable outcome for the survey. The promoter of the survey, the contractor that promoted the survey, had kind of convinced the zinc-lead explorers that they would get this marvellous new data set that would drive their exploration in new directions. And so the project promoter, some of whom I'm sure you know, said, right, well, this is no good. We're going to hammer this data set until we get some good stuff out of it. And courtesy of a chap called Ian Campbell, who's one of these nerdy lifelong data processing people, they went to work and just to extract the last little bits of information out of the data. So that hard work, obviously taking the farm infrastructure out of the data, removing regional gradients, reduction to pole, and separation filtering were the heavy-duty things that we've done to this data. I'm not going to talk individually about the processes. I'll touch on them. And for those of you who are involved in seismic, perhaps say that reduction to pole is a process that does similar things with magnetic data to what migration does on seismic sections. It puts things more in a more correct space than the measured data. So after all that, we get something that it's interesting. It's not clear cut. It's messy. It's fuzzy, but it's interesting, and there's lots to work with. And given that it was a sedimentary basin, the application of separation filtering became part of the push to get more out of this data set. And separation filtering, I should say, before we start doing separation filtering, that filtered working data set that we started with had an intensity range of only 5 nanoteslas. So after we removed the culture and the regional gradients, we've really only got 5 nanoteslas to work with, and that's actually a pretty small amount of data. The separation filtering basically identifies rock bodies at different depths in the subsurface. So if we have different groups of magnetic rock bodies, different depths, the separation filtering will allow us to identify them, and if we're lucky, separate out their responses from each other. And we'll see another example of that later, but in this example, there was obviously a shallow signal and also a relatively strong signal that was sourced at circa sort of 300 to 450 metres. So we had a deeper signal and a shallower signal to work with, and our process is the same as what I illustrated at Pine Creek. It starts with observations. It starts I guess before we do observations, with getting ourselves tuned into the local geology as much as we can. And the local geology, as you can see, has a reasonable amount of detail around the mine areas, which is determined mainly from drilling, and not much coherence away from that. So there's not much at surface to work with, but what there is, we're obliged to digest and be aware of before we start doing our mag work. And here's our basic observations done on the shallow signal from that that map data. You can see that again it's messy. Things are not particularly clear or coherent. Boundaries are often very vague. Some of the linear breaks are discontinuous, and some are even conjectural. But again, it's just a bunch of observations. You look at the data, you spend time with it, say, well, I can see this, and I will record this as I see it, without necessarily having a fix on what it is geologically. Let me just do the observations. And having done that, we can take into account whatever geology is there. Some of it's fact, some of it's conjecture, a little bit, and some of our observations might be a little bit conjectural, but pull those together into something that looks like a solid geology map. And so here's the rough version, here's the draft version. Take that forward with a little bit of geological thinking and a lot of cartography to make it look good, and we have something that is workable in an exploration sense. Now, I talk a lot about what this might mean for exploration, and it's an interesting story. Bottom line really is that having added that magnetics, we now have a much more coherent flowing view of the geology in the near surface. So the coherency of the structure, even the coherency of the stratigraphy and possible fault structures is clearly expressed in this. It's still this is, I have to say, this is still not ratified with a whole bunch of fieldwork, but you can see by adding the magnetics, we've taken the picture a long way forward, and the associations that we might see or hypothesize around the mine areas are actually important. And we can, okay, said that. Yep. We do the same thing with the deeper signal, and it's different, and it's not just a fuzzy version of the shallow signal. There are actually quite strong and coherent and different patterns that we can see in that deeper signal. Again, there's an observation layer. There are a whole bunch of sometimes clear, sometimes a little bit fuzzy features that we can see, but we do the observations, and with a little bit of knowledge from the geology and the experience that we've developed from working at the shallow level, we can put that into a grubby-looking draft interpretation and clean that up into something that then is a much more workable, presentable product. And again, it's telling a story that seems to have some associations with structure, stratigraphy, and the mineralization. So I have to kind of reiterate that we've not been lucky enough in this area to be able to post our work on the area to go into out to Gelmoy and test these ideas with drilling. The area is essentially abandoned. It's not being mined at the moment, so we haven't had the opportunity. But if we look at it from the point of view about our start point with geology, we've added the aeromagnetics, and now we have a very, very good and presentable working hypothesis to drive our exploration forward. 4 minutes. Oh dear. Okay. Let me just jump forward and say the message there is that very weak magnetic signals can provide very strong geological input. I didn't think I was speaking that slowly. Okay, 4 minutes. The Amadeus Basin study is quite similar. It's a routine oil exploration case study there. And let's look at just the locality. We're going to be concentrating on this small area. In here, you can see the fuzzy expression of the basin, the more detailed expression of the basement rocks. Again, we've applied this separation filtering. I won't talk to the technique of that, except to say that it's old established technology, and also to say in this area and in any sedimentary basin work that we do, the quantitative side of things is very important. So we can't just draw some squiggles and hope. We have to apply a range of quantitative tools, automatic depth estimation, and also, of course, routine forward modelling. I'll whiz through this a little bit quickly. What I'll say to all people is that if you would like a copy of this presentation, it will be available to anybody who emails me, and I'll give you a link to download it. So I'll whiz through the Amadeus reasonably quickly. It's a reasonably routine case history. Start point, as you can see, is mainly sand dunes, not much exposed geology. Some interesting folds in the outcrop that we can see. As we saw before, we have some high-frequency shallow stuff, which looks like it's got some coherency in near-surface geology, and some deep stuff that looks really deep, superimposed on one another. So our approach to that is to isolate the shallow from the deep. In this case, the second derivative is the image that expresses that shallow stuff well. Once again, our approach is to do basic observations without knowing exactly what they mean. Let's just get an observation layer and integrate that with the known geology to build our first working story. And as you can see, if we compare the start geology to our kind of working hypothesis, pardon me, shallow picture, there's a raft of new information to work with. We then go to the deep, and the geometry is completely different. The depths are large. The separation filtering is telling us that the signal is concentrated around 9.5 kilometres, which probably means there's sources at 6, 7, 8, 9, 10, 11, 12. And those geometries are quite different to the shallow stuff. We can quantify those depths with some modelling and also some automatic depth computations, as well as draw our funny little lines and squiggles. So these yellow polygons and red polygons in these lines are our basic empirical observations. The numbers here are the depths from the quantitative computations, and we come up with a geometry that it's interesting. We don't know what the rocks are. They're 10 kilometres down or so, but we can record the geometries and try to understand the structure of those things, and put that together with the shallow picture, and it's pretty hard to make sense. What we can say here is that the geometry of the deep stuff has very, very little influence on the geometry of the shallow stuff, and there's reasons for that. What we can say here is if we try to impose those depths that we determined from the deep work as the basin architecture, we'd be wrong. And the important thing here is that we've gone to a geological thinking stage of trying to understand what's going on with the shallow and what's going on with the deep, and finding that there are certain structures, certain faults that have propagated up through and been involved with the shallow stuff, but mainly the deep stuff is not influencing this shallow stuff. And then there's a detachment zone through here, which comes from I guess it's inferred from our geological thinking. So it's not automatic depth calculation, basin architecture, end of make story. It's shallow observations, deep observations, head scratching, how does this all work, and working towards okay, what we're going to do with this. And to finish off this example, what did we do this for? It's an oil exploration play. It's an area where there's almost no gravity, no seismic, but plenty of potential. We're going to shoot seismic here somewhere. And what the MAG has done for us is produce a geological document that hypothesizes some pretty interesting plays, and obviously we've integrated the local plays into our thinking and defined, as we did with the Pine Creek thing, some target areas, which then allow us to plan our first seismic survey. And the end point then is, well, if we hadn't done that, if we hadn't brought the Aeromag in, how are we going to target in that area? We brought the MAG in, it's relatively cheap. The time scale and effort scale of interpretation is not that great, and we've got very focused targets. So the message there is that in sedimentary basins, that MAG has the capability to generate structural stratigraphic targets, basically to allow us to focus and plan our initial oil exploration, which is obviously going to be seismic. Okay, I'm on the last run now, and I'll be trying to make time for this because this is the Australian banner waving. The impact of MAG in Australia has been pretty profound. The Federal Bureau, which was then the Bureau of Mineral Resources, started flying 1 mile spacing in the 50s on an experimental basis. In the 60s, we had a nickel discovery, which created a nickel boom, and that data, which then was analog and is now being digitized, actually drove that boom. It told the explorers where the ultramafic rocks were. And if you look at the pattern of exposure, without that MAG, the nickel boom would have suffered greatly. So there was that 1970s phase of, wow, this really coarse MAG stuff is driving nickel exploration, and it drove much success. Then came a gold boom in the 1980s, centered around Kalgoorlie, and this same data helped us to kick that off and drive it. But obviously 1 mile spacing is pretty coarse, and the geological value of that data was recognised to the point where we started flying 200-metre line spacing over the main gold exploration areas, and that created pictures like this. And here's the Golden Mile, so we're talking 80 million ounces, and the pale green areas here are not much exposure. So you think of in the exploration context, how are we going to push forward our gold exploration into the airborne magnetometer? And this is 200-metre data, scale bar here, and you can see, wow, we've got a lot of information to work with. But that information doesn't actually have much value until you take the time to build your geological interpretation. And I can say that that phase of, say, 200-metre flying in the goldfields spruiked an Australia-wide and then almost worldwide thing of much more detailed flying in gold exploration and other exploration environments. That thing spread, and in the 1990s, our governments picked up on it, and if you like, a countrywide program of coverage of 400-metre spacing was driven. I give credit to South Australia for driving that. It was a game changer for them. They decided to do it because they were getting almost none of the exploration expenditure in their state. They said, right, we'll fly 400-metre day of the whole state, and not only will we make it available to people, we won't charge them. And not only will we not charge them, but we'll actually take it to their offices and put it in their offices and say, please use this. And that really was a game changer and caused, I'm going to say, 5 very significant discoveries that well and truly paid for that program. And that's kind of led now to what we call GADS, which is the Australia-wide database, where all of this data is now free and downloadable. Much of it is 400 metres or better. There's also gravity, all of the gravity, radiometrics, and there's other stuff. And this is all free, downloadable to anyone. And it's an absolutely stunning resource and has made the latter years of my career absolute heaven. And just to finish off, where are we these days? I touched on mind scale flying. The push, certainly from mineral explorers and say groundwater explorers, is more detail please, more detail please. And 25 metre, 20 metre spacing is doable much more broadly than you would first think. There are fixed wing platforms, crop dusters, yes, helicopters, yes, and also now unmanned devices. The bottom line, though, is that the amount of stuff that it delivers, the amount of information it delivers, is stunning. The amount of detail that you can see at geologists' working scales. But it doesn't achieve its value until we go through that phase of observation, interpretation, head scratching that takes time. And so I guess the last word is that mag data should be a driver in exploration and mapping over different scales and things, but the value is not realised until we go through that process of integration and interpretation. And thanks for your interest. And I thought I had it well down under the 45 minutes, but clearly not.
Dave, that was an incredible tour de force. This is in fact just a taster for the book, which is an order for